Okay, I think we're going to get started. It's a great pleasure to be able to introduce this afternoon's seminar speaker, Ms. Libby Orr. Libby's a native of the hamlet of Lesterville, Missouri, which I rechecked this morning, and it's in the hilly southeast part of that state, adjacent to the Mark Twain National Forest. But lots of places in Missouri are adjacent to the National Forest. You look at the map, you'll see what I mean. But Libby attended the University of Missouri as an undergraduate and earned her degree in atmospheric sciences there in the spring of 2022 with minors in geography and astronomy. She found herself gradually attracted to synoptic dynamic meteorology throughout her time in Columbia. She's not one of those people who has a seminal event that said weather is my thing. She always was interested in it. And she studied gravity waves and winter storms using the WRF model with my friend Pat Market down there. And in her senior fall, this is an interesting story, in her senior fall, she kind of remotely attended a seminar that I was giving at my alma mater at St. Louis U. I was invited to go down there and talk about waviness of the Northern Hemisphere wintertime polar and subtropical jets. So we didn't meet, but I knew that there were people online. And then around the same time, Libby was applying to graduate schools, and as it turns out, she applied to our department and arrived here in the fall of 2022 and began working on a necessary extension of the very work that originally connected us, namely investigation of the Tropopause-Level jets, but during the warm season. And I'd been harangued by my European colleagues to finally do the warm season, and so when Libby came, that's what we did. And I think, many of you probably think of Libby as a meticulous, soft-spoken, hard-working scholar, and I'd agree that those are correct impressions. However, after getting to know her the last couple of years, I would say that this first impression, compelled by her placid facade, betrays the steely-eyed competitor residing within. And she's played competitive volleyball for many years and brought that activity to our department. And I have heard of, but unfortunately not yet witnessed, episodes of fierce determination in the face of seemingly insurmountable odds. Even yelling at refs has been alleged. Of course, even yelling at refs has been alleged. And of course, I've seen my own decidedly nerdier examples of that same core personality trait, as when this summer, Libby rewrote my 30-ish page Fortran Gempack code monstrosity for conducting some of the analyses that we'll see today. You don't have to shake your heads yes. Conducting some of the analyses you'll see today into a 1.5-page collection of Python commands that she says does the same thing. I'm not sure it does. As any good athlete will be wont to do, the completion of this project, in very short order I should add, was announced with a notable helping of trash talking from Libby and aided by my group. But it's been really enjoyable working with Libby over these last couple of years, and we hope to do some more in the future. And so without further ado, Libby was going to tell us today about characteristics of the Northern Hemisphere warm season Tropopause-Level jet and associated trends as revealed by 3 Reanalysis datasets. So take it away, Libby.
Thank you, John. Can everyone hear me okay, first off? Awesome. So, welcome. Thank you for coming. Today, we're going to go on a little bit of the journey through my past 1.5 years of master's research, which, as John had just said, has taken the form of the characteristics of the Northern Hemisphere warm season Tropopause-Level jet and its associated trends. But before we dive into all of those specifics, we need to set an early precedent, a base idea of what the jet stream is. So, as I'm sure most of you know, jet streams are just rapidly flowing currents of air that reside near the tropopause. So, super fast regions of air at the top of our troposphere. They are present in both hemispheres, as we can see from this diagram here on your right. And in this case, this image demonstrates 2 jet streams per hemisphere, a polar jet stream and a subtropical jet stream. And these structures influence climate on both a regional scale and more smaller scale weather patterns. So you can have influence in things that are larger and smaller, a bit of the best of both worlds. And with these structures, they change seasonally. Depending on the season, they can change in their intensity and location, depending on the hemisphere as well. So, in specifics, if we look at the 2 main types of Northern Hemisphere Tropopause-Level jets, as was demonstrated in the image that was on the slide before, there's the polar jet, also called the eddy flux jet, because it results from eddy momentum flux convergence from mid-latitude baroclinic waves. And so because of this, it's tied to high latitude baroclinicity, And so therefore, it generally resides in the mid-latitudes, really about north of 40 degrees north. And in vertical, it resides around 300 hectopascals. The other type of jet is the subtropical jet stream. It results from angular momentum transport that we see as a result of Hadley cell circulation. And so, as you might expect, it resides at the poleward edge of this Hadley cell around 30 degrees north. And in the vertical, it resides around 200 hectopascals, so a bit higher than what we saw with the polar jet. So the references I've included in this slide, and a few others I'm going to mention here in a second, like to focus on how these jets evolve throughout a calendar year. However, in prior studies, they tend to generally focus on these jets only in the cold season. So in our case, the Northern Hemisphere winter season. But there's little sources, really not much about how these jets behave in the summertime, in our Northern Hemisphere warm season, which is what we're going to dive into today. But first, I would like to discuss some of these previous jet identification methods that other scientists have done. One of the largest contributors to this topic is Gloria Manny and her research group. She developed her methodology in this first 2011 paper. However, they have published many papers since then. The ones I've listed on top are only a small example of all that her group has done. And their methodology consists of this. They take their data sets, they look through all of the grid columns, and they only retain grid columns in which wind speed in the 400 to 100 hectopascal layer is above 40 meters per second. So where winds in the jet layer qualify as jet speed winds. And they do this in select latitude and longitude slices. So they pick their certain regions of the globe they want to look at. And so once they find these regions of winds that exist above 40 meters per second, they apply further criteria, especially if these jet core regions exist really close to each other in space. So to be considered two separate jet cores, if these high wind speeds are next to each other, these jets, as you can see in this image from their first research paper, must be at least 15 degrees separated, whether latitudinally or longitudinally. In this case, they look at the Southern Hemisphere latitude. So the winds in this image are represented with grayscale, and we have our two jet cores in these darker colors, and they're decently separated latitudinally. So we fit the criteria there. And then their second criteria is that these two cores have to be separated by a dip in wind speeds. In this case, winds less than 25 meters per second, which is also demonstrated in where we have these lighter colors showing lower wind speeds. So in this image, these are two separate jet cores. And so following this methodology, whenever they found jet cores, they kept track of temperature, potential vorticity, relative vorticity, and several other characteristics to kind of get an idea of how these jet cores behave. However, they looked at this on a year-long scale, but ultimately in this first 2011 paper, they made no major conclusions about the Northern Hemisphere warm season. They focused mainly on the cold season for the Northern Hemisphere. Another different kind of method comes from the Archer and Caldera 2008 paper, which they still considered the 400 to 100 hectopascal layer, but they looked at mass-weighted average wind speed instead. So a bit different than what the Manny group decided to do. And through this, it allowed them to characterize jet speeds, the pressure level of jet cores, and their latitudinal locations. So several different characteristics from this method. Currently, a bit of a newer method comes from Christenson et al., 2017, where that paper built on the methods seen in Koch et al. And developed a method to place jet streams into their relative isentropic housings. So where these jet streams lie in isentropic space. And what this did is that it provided framework to objectively identify these Tropopause-Level polar and subtropical jets separately. So to do this, they also looked at the 400 to 100 hectopascal level, as was demonstrated in Koch et al. As kind of the base for a lot of jet papers. And they considered integrated average wind speeds in this layer, instead of just looking at wind speeds on its own. I will dive more into this methodology in a second, because this Christenson et al. 2017 methodology is also my methodology. So hang tight, and I'll elaborate in a second. And this leads us to my first research goal part 1, which is to apply the analysis seen in the Christenson et al. Paper to the warm season. In this paper, they only covered the cold season. We want to know what happens in the warm. And to do through this, it will allow me to examine the jet stream distributions and their isentropic calories in the cold season. So, let's dive into it. First, though, I need to tell you about my data and a deeper dive into that Christenson et al. Methodology. So first, like I said in the title, we focused on 3 different reanalysis data sets, the NCEP, JRA55, and ERA5. The NCEP time frame I trimmed to 1959 to 2019, and it comes in at the coarsest grid resolution of about 2.5 degrees. JRA has the same time frame, so 1959 to 2019, but a bit of a finer resolution at 1.5 degrees. And then finally, our ERA5 dataset has a shorter time frame of 1979 to 2019 at our coarsest grid resolution of 1 degree. However, for purposes that I will reveal later on in the talk, we regridded these 2 datasets to match NCEP at a 2.5 degree resolution. So, once I had all my data formatted and ready to go, I followed the methodology from Koch et al. And Christenson et al. In tandem, and I was able to identify the isentropic housing for each jet stream. So to do this, once I had my data set, I searched through all of the grid columns and found the point of maximum wind speed for each grid column. At this point, I pulled the corresponding values of theta and the pressure values for this region of point of max wind speed. And then after I had all those values, I went through all of my grid columns another time and removed any columns in which the integrated average wind speed in the 400 to 100 hectopascal layer was below 30 meters per second. So that removes any grid columns that don't contain a jet stream, basically. And so once I have all of these columns that qualify as containing a jet, I can take them and group them into 5 Kelvin bins. And so what that does is it produces charts same like this one from Martin and Norton 2023. They followed this same methodology just in the Southern Hemisphere winter. And so what this does is that the more qualifying columns I have in a 5 Kelvin layer, the higher these histogram bars are going to be. So in these red columns, you can see where it reaches a peak. That is where the subtropical jet resides in the Southern Hemisphere wintertime. And in this case, that is in the 340 to 355 Kelvin layer. Similarly, if I look at the blue columns, we can see where they found the polar jet to reside. So this peak is a little shorter, but it's still there nonetheless. And in this region is where the 310 to 325 Kelvin layer is where the polar jet resides in the Southern Hemisphere. So I can get these distributions of where the jet is in isentropic space from this methodology. And where did that take me? So to start off, I recreated results from Christenson et al. They covered the cold season, so they produced plots that look like this. And in this case, we have 2 distinct peaks in all of our cold season months. The blue, indicative of the polar jet, and the red, indicative of the subtropical jet. So 2 distinct peaks in the cold season, a bimodal jet distribution. There is a little bit of a peak further out here at higher isentropic levels, but that's just the polar night jet. We're not worried about that for right now. And so you can see, not only do we have these peaks, but they're also decently separated by a minimum in columns in the middle isentropic layers, except for November and April, where the 2 layers happen to be right next to each other. So let's look at these months in turn. Just to further drive the point home, here are the core cold season months, December, January, and February. You see, we have 2 distinct jet layers. We have a solidly bimodal distribution. This y-axis is the fractional amount of columns, so the amount of qualifying grid columns out of all total columns. So in this case, in our polar jet layer, 27% of all qualifying grid columns seen in this plot belong in the polar jet layer that's been selected here. Similarly, in the subtropical layer, 30% of all grid columns reside in the subtropical jet layer. So in total, that means 57% of all qualifying grid columns reside in these two defined jet layers. So majority of our qualifying columns that we found reside in a jet layer. Now, you might remember that I talked about how April and November looked a little different than the other 2 months, right? They're both still bimodal, yeah, but they're a lot closer together than we saw in the middle of the cold season. April, there is no minimum between our two jet columns. They're right next to each other. In November, there is a little bit of a separation, but that's only a 5 Kelvin layer. It's not as drastic as we saw in the middle of the cold season, which is kind of weird, right? Why are these months so different when compared to the cold season? So I took these months and I broke them down daily. So this is April up first. And so April 1st signifies the end of our cold season. And then we go to the 10th, 20th, and 30th, which signifies the start of our warm season. So we can see how our jet distribution evolves through the course of April. And so starting out April 1st, we have two very distinct jet layers. We have our polar jet and our subtropical jet, and they're separated by a decent minimum. If we go to the 10th, we still have our two jets. However, they've gotten a little closer together. And then by the 20th, our jet layers are right next to each other. No separation whatsoever. By the time we reach April 30th, we see a unimodal jet distribution. There are no longer two jets in the Northern Hemisphere at this point. We see a switch to unimodality, and I've changed these colors to purple to signify that there is a unimodal jet at the end of April, at the start of the warm season. Okay, that's kind of weird. What if we consider November? November is the end of the warm season, and we see a transition to the start of the cold season. It tells the opposite story. We start out seeing a solidly unimodal jet layer in November 1st. That layer is still unimodal on the 10th, even though it's shifted a bit to lower isentropic layers. And then by the 20th, we see a stark return to bimodality. We have both of our jets again, the polar and subtropical, and they're separated by that minimum. And we see a return to that on the 30th and into the rest of the cold season. So with this unimodal jet being present on the end caps of the cold season and the warm season, what might the summertime look like? Well, this unimodality persists through the entire summertime as well. We start with May, we have a solid unimodal jet. It resides in the 330 to 345 Kelvin layer. By the time we get to June, our peak gets a little more concentrated, and we do move up a little bit in isentropic space. By July, we have a very concentrated peak, very high. 61% of all of our qualifying columns reside in this jet layer, and we're still in the same isentropic layer. By August, same story. We have a very concentrated peak, same layer. And then by the time we get to September, we're starting to cool down. We're past peak warm season. Our peak does decrease a little bit, and we go down a little in isentropic space. And then finally, in October, our peak goes down even further, and we go down even further in isentropic space. So if we look at this in the full terms of calendar year, we've completed our full jet timeline throughout the course of the year. We start in January, middle of the cold season. We have two distinct jets, polar and subtropical, bimodal distribution. And it persists all the way until April, when these jets layers get a little closer together, and then by May, we have transitioned to a full unimodal jet. And then this unimodal jet seems to strengthen by the time we get to the middle of the warm season. And then after we pass that peak, it goes down a little bit until we finally reach November, where we switch back to our bimodality and finish out the year solidly bimodal. So since there's such a big difference between seasons, I took these and pulled plots from middle of the cold season. So this is NCEP data in January, and the middle of the warm season, so July. You can see there's a really stark modality difference. There are fewer qualifying columns in summertime in general. However, so that's why you have a bit of a less widespread. However, the story still holds. Very different modality, our peak in the summertime is much more concentrated. If we look at this in terms of isentropic space, you can see our polar jet in the Northern Hemisphere cold season resides in 310 to 325 Kelvin layer, and our subtropical, a little warmer, in 340 to 355 Kelvin layer. If we look at our unimodal jet, it kind of resides between those two. It lives in 335 to 350, so it's shifted a bit warmer than the polar jet, but only a little bit cooler than the subtropical jet. Because if we overlay these two plots, you can see that the wintertime subtropical jet and the warm season unimodal jet seem to share isentropic space, which may give us an idea in later research as to where this unimodal jet arises from. So I did this to all of my data sets. This is the GRA calendar year distribution, and it's almost nearly identical to what we saw with the NCEP data. We still have the bimodal distribution in the cold season, and we switched to unimodal in the warm. And then finally, with the ERA data set, different data set, same story as before. We're bimodal in the cold season, unimodal in the warm season. So good agreement among all three of our data sets. So if you remember this plot that I showed you before in the introduction slide, showing that we have a polar jet stream and a subtropical jet stream present in the Northern Hemisphere potentially all year round, we know that this is now not true in the Northern Hemisphere warm season, right? So we can only use this picture if we're talking about the cold season in the Northern Hemisphere. So I took all of the different isentropic housings for each of our jets, whether it be polar, subtropical, or unimodal, and put them into this handy chart. You don't have to remember all of these numbers. I don't even remember all of these numbers. But the main takeaway I want you to have from this is that everywhere where all the boxes are white is where the data sets agree on the isentropic housing of that respective jet. Where it's red is where that particular data set disagrees with the other two. So if we want to do some quick math, there are 54 total isentropic housings across all three data sets, and only 6 do not match. So that comes in at about an 89% agreement among 3 different data sets, which is pretty good. I'll take that. And so now that we know where our jet is housed in isentropic space, we can start thinking about the different characteristics of this warm season jet. So that's going to take the form of things like jet waviness, or the speeds of the jet core, or things like latitudinal placement. But first, we need to dive into more methodology for a bit of a different approach this time. So, another more recent methodology comes from Merton 2021, and he used the cold season isentropic housings that came from the Christenson et al. Paper, and applied a metric to assess waviness of these cold season jet streams. And to do this, he searched for this thing called the core isotel, which we'll talk more about here in a second, but you can imagine it as like the spine of the jet stream on any given day. And he also used the average latitudinal displacement methodology, which I'll also go over, because this is also my methodology. But first, to do this, to find the spine of the jet, we need to start off by considering the quasi-geostrophic potential vorticity equation, which is given by this equation on top. And if we take this equation and rewrite it using lambda as the second order differential operator acting on phi, we can condense the QGPV into the smaller term that you can see over there on the far right. Now, as a result of doing this, we can directly relate the cross-jet gradients of PV, QGPV, given by this term, to geostrophic wind speed by substituting in the natural coordinate form of geostrophic bounds. So once we have this equation, we are allowed to now make the conclusion that cross-flow gradient of QGPV is directly related to geostrophic wind speed. Or, if we want to consider this in a bit of simpler terms, large horizontal gradients of Tropopause-Level PV are associated with local wind speed maximum, as was first suggested by Cunningham and Kaiser 2004. So, now that we know this relationship, we can also conclude that jet cores coincide with regions of strong PV gradients. So in this case, my jet core, the region of faster wind speeds, is highlighted by this blue region, and my PV contours are in these reds. These PV contours we are going to call isoterms, and jet streams tend to flow along these isoterms. So we can start to consider a proxy for the axis of the jet and call it our core isoterm, because it cuts right through the core of our jet. And it's highlighted in this example by this now green contour. So how are we going to objectively identify this core isoterm, since it's going to prove to be so useful to us? Well, if we start out and consider all of our isoterms on any given particular day, we know that our jet core resides in a region of these tightly packed isoterms. So if we search through all of them, from 0.5 PVU all the way up to 5 PVU at a 0.1 PVU interval, and calculate the circulation per unit length along each of these isoterms, we can find the isoterm along which our circulation is maximized. This is why I regridded my data, because we have to consider contour length and then circulation and various calculations from that. So if I didn't consider my data on a uniform grid spacing, it would get all messed up and then just be a disaster in the end results. So this is the circulation theorem we used, and we can now define our core isoterm as the PV value along which circulation per unit length is maximized. So just as a quick example, this core isoterm varies given on any particular day, but in this case I pulled an example from June 15th, 1995, from the jet in the 335 to 350 Kelvin layer, and so this black contour represents our core isoterm for that day. It has a PV value of 2.5 PVU. And you can see in multiple cases it intersects various jet cores, because the green and blue shading represents wind speed. And so it intersects various regions of wind maxima, but over the Pacific Ocean, this is where the jet on this day reaches its maximum speed, and our core isoterm cuts right through that area. Perfect. If we look at the PV gradient as well, in this image on the right, you see there's a decent gradient and spread of PV on this given day all across our hemisphere, but the region where we have the tightest gradient is also over the Pacific Ocean, the same spot where we saw that wind speed maxima, and our core isoterm cuts right through that region as well. Great. This is exactly what we needed for analysis further on. So, yeah, core isoterms and their values vary on any given day, right? The jet is always changing, so will our core isoterm and its corresponding PV value. So I calculated the core isoterm PV for every day in all of my data sets in the warm season, and put them into this distribution. So the orange is the NCEP data, and you see it's a bit more concentrated towards lower values of PV, especially here. It has a mean core isoterm PVU of about 1.85. And then if we look at our other two data sets, they have a much wider distribution, right? They don't have that super concentrated peak that we see in the NCEP data set. So first, if we look at ERA in this green, it has a mean core isoterm PVU of 2.41, and then our GRA 55 data in this purple has a core isoterm PVU of 1.85. So a bit of spread and amongst our three data sets on the mean PVU of our core isoterms. However, overall, these mean values are still within 1.2 PVU of each other, which isn't bad, considering all the different physics and everything else that can kind of go into making these different data sets, right? So we'll take it. So now that we have established this core isoterm and we can plot it for any given day, we can start to consider the waviness. So waviness is going to take the form of this average latitudinal displacement, or ALD, and I tried to break this down into a base example. So if you pretend this blob up here is a core isoterm on any given day in the Northern Hemisphere, we can calculate the area that is contained within that core isoterm on the globe. Once we have this area, we can also calculate the latitude of a zonal ring that encompasses an equivalent area. So my blob on top and this perfect red circle on the bottom have the exact same area, even though it might not look it. And so in the real world, these will be overlapped, and we can measure the meridional displacement of the core isotope from its equivalent latitude at each longitude. So you can see the different displacements in these blue contours where the jet is displaced equatorward and where it's displaced poleward in the green lines. And so once we have this measurement, we can sum the lengths of all of these meridional segments and divide them by the number of longitude lines at the grid spacing of my data set, which, since I'm at a 2.5 degree grid resolution, is now 144. And so once I get this number, it gives me a measure of the ALD in degrees, a measure of jet waviness based on its core isotope. So if we return to the image that I showed you all before, this is still that June 15th core isotope, except now in this dashed red circle that represents the equivalent latitude of that jet, which on this day is 34.9 degrees north. You can see where it's displaced from this equivalent latitude. On this particular day, our jet has an ALD value of 5.56 degrees. If there happened to be a day where we had a perfectly zonal jet, so a jet that was just one complete big circle, it would exactly match its equivalent latitude and have an ALD of 0. So the higher the ALD, the wavier our jet gets. Which leads me to my research goal part 2, which is to apply the analysis method seen in Martin 2021, which I just explained to you, to the warm season, which is going to allow us to get and assess the various characteristics of our unimodal jet. So, starting off, this is the warm seasonal average latitudinal displacement, so our jet waviness in the May through October time period. And if we start with our NCEP data, you can see there's a decent amount of interannual variability, but the NCEP data tends to stay around 7.5, maybe getting up to 8 degrees ALD by the end of our time series. So just eyeballing it, it looks like it features a jet getting wavier. If we add on the ERA data, it features lower ALD values, starting out around 7, maybe getting up to 7.5 by the end of our time series, but still lower overall than what we see with NCEP. And then finally, if I add in JRA 55 data and its corresponding trend line, it kind of goes right down the middle. It's got a decent amount of interannual variability, and it doesn't really seem to have much of a trend. It is promising, though, that across all 3 data sets, the interannual variability does kind of line up, right? So where we have peaks, all of our data sets have a peak, and where we have troughs, all of our data sets have a trough. So that's nice. Like I said, according to JRA data, at least, our ALD exhibits a weekly positive trend. And I pulled the p-value from this trend line, which came out to 0.38, which is not significant. So according to JRA 55 data, our jet isn't getting wavier or less wavy, it's staying about the same. If we move on to jet course speed in the same time frame as before, once again, NCEP data seems to have a stark trend in increase, right? We start at the beginning of our time series, about 56, 58 meters per second for the speed of our jet core, but by the end of our time series, it increases all the way up to almost 62. So a pretty decent increase seen from the NCEP data. If I add in my ERA data again, it doesn't have as much of a trend. However, it still has values that are much higher than what we saw with NCEP. So it favors a jet whose speeds are around 63 meters per second. Pretty fast. And then, once again, if we add in our JRA data with the trend line, it matches almost identically to our ERA data, especially in the latter half of our time frame, which is nice. If we look at our trend line, just kind of eyeballing it, it looks like it's increasing a little bit, but if we pull the p-value from that trend line, it's actually 0.09, which means it is significant at the 91st percentile. So according to JRA 55 data, our jet core speed in the summertime is increasing. finally, if we look at the seasonal average equivalent latitude, so the latitude has the equivalent area as contained within the core isotel. NCEP has a lot of interannual variability again, but ultimately it features a jet that resides around 42, maybe getting up to 43 degrees north by the end of our time frame. Once again, adding in ERA5 data, it's once again different from NCEP. It features a unimodal jet that's a bit more equatorward, coming in at about 40 degrees north. And then finally, if we add in JRA data with our trend line, it kind of hits right in the middle of these two, closer to ERA data, but still not really getting up to 41 degrees north. So between 40 and 41 for JRA. And if we look at our trend line again, pull out the p-value, it has a value of 0.51, which is not significant. So our jet isn't moving poleward or equatorward in the warm season, it's kind of staying in the same region. So, I know that was a lot, but some conclusions. The biggest conclusion, in my opinion, is that the warm season is dominated by a strongly unimodal jet distribution. There aren't two distinct polar and subtropical jets like we see in the winter time. Similarly, April and November serve as transitional months between modality. So in the case of April, we see our jet distribution go from bimodal to unimodal. And the opposite happens in November. And across all three of the data sets that we looked at, the jet occupies nearly identical housings in the warm season. The only data set that's the most different is the NCEP data set, but it still only had two different variables. And then finally, if we refer to our trends, the JRA55 data set features a statistically significant modest increase in jet core wind speed. So it features a jet that is increasing in speed with time, albeit modest. While I didn't show it to you, the ERA5 data actually features a statistically significant, increasingly wavier warm season jet. So while we didn't see it in the JRA55 trend line, ERA5 thinks that this unimodal jet has gotten a lot wavier with time. And then finally, as we saw, NCEP data was commonly outliers. They didn't really, while they followed the same interannual patterns and things, their overall values were really off, which may be just a testament to the quality of the NCEP data or something similar. So, with all of these big conclusions comes a lot of future work. Firstly, I'd like to look at April and November transition trends on a yearly basis. So have these always been the transitional months? Or, we're in a warming climate, so maybe in earlier times, this transition occurred in, say, May instead of April. I would like to look at the waviness differences, so the ALD differences by basin. So what this might look like is if I take this day, for example, and cut it into the Pacific Basin and Atlantic Basin. Just looking at those lines, their waviness differs. Are there trends with that? Is the, just for a random example, is the Pacific always wavier than the Atlantic, or something like that? It would be interesting to investigate. Similarly, I'd like to look at changes in the wind speeds along the core isotel. So if we look at the same example, I put in these dots right where we have the wind speed maxima and the location of these wind speed maximums. But how do they change and evolve over years or months or seasons in general? Are they always going to be located over the Pacific? Will they always be located off the coast of the U.S.? Are they always, do they always have the same intensity, same location, stuff like that? And then finally, an idea I've been kind of throwing around is, does this single jet behave similar to a jet superposition? So in the Christenson et al. Paper, their main focus was on jet superpositions. And so what these are is, in the cold season, when we have two distinct jets, they can kind of overlap each other in vertical space, like be stacked on top of each other. And when this happens, we see a strong increase in winds in this superposed jet. And so if I compare my seasonal average jet core speed for my unimodal jet in the warm season versus the jet core speeds for the polar and subtropical jet in the cold season, seen from the Norton 2021 paper. You see there's a pretty solid difference in wind speeds. This unimodal jet, if we look at the data sets that tend to agree more, hangs out around 63 meters per second. But if we look at the fastest jet in the cold season, which is a subtropical jet, its trend line never really crosses 50 meters per second. So there's probably a few different ways we could explain this maybe, but I'm interested to see if this summertime jet behaves as a superposition. And so, that's all I have. But I have some acknowledgments first. Shout out to my advisor, John, for helping me get this far in my career, and also putting up with me bragging about Python all the time. My committee members, Angela and Steph, the Martonian lab, for you guys who helped me make it this far. And that also goes for the group of friends from AOS that I've been able to form. I wouldn't have made it this far without any of you all either. And then that also goes for the entire grad student cohort, who have all been super welcoming and have made my transition into coming here a lot easier than it could have been. I'd also like to thank my parents, Michelle and Joey, for putting up with me moving states and now living in Wisconsin and driving all the way here to see me today. And then the entire AOS faculty and staff. None of us would be able to do any of our research or anything else if it wasn't for all of you guys. And so with that, this is my email. This is where you can find me. I'll take any questions. Thank you. Jack.
I can go first. Someone has to. So it seemed like you spent a long time or a good amount of time at the start, talking about what makes or how to identify what the subtropical jet is and what the polar jet is. I'm just asking this question because I'm taking the machine learning methods class right now. Have you ever thought about trying to just play within the data and see if you can find some sort of machine learning method or algorithm to sort out what those differences are versus using what already are predetermined kind of bidding systems, I guess?
I haven't, though it does sound like an interesting idea, for sure. I'll have to consider that. Whoa, Grant.
I got a couple.
Okay.
First, you showed a bunch of weak trends for all the warm season stuff. Was there, in John's paper in 21, were there trends for the cold season stuff that you were looking into that?
Yes. Let me see if I put these in my extra slides. I did. So I showed you the speeds, right, when I was talking about superposition. This unimodal jet is a lot faster than what we saw in the cold season. But it also had, a trend, at least in JRA data, that the jet's getting faster. In the cold season, the Martin paper found no specific speed trend for either of the jets, polar or subtropical. If we wanted to look at it in terms of waviness, so with ALD, my unimodal jet, at least in JRA data, didn't have much of a trend. In ERA, it did see an increasingly wavier jet. However, for each of these respective jets in the cold season, they did see an increase in waviness, both of them. And then, in terms of equivalent latitude, whereas my summertime jet kind of stayed at the same latitude, Martin 2021 saw an increase in both of them. Both of these jets are moving poleward, it seems. However, the polar jet is moving poleward at a more drastic rate than what we saw with the subtropical jet.
And it's the only one that's statistically significant.
Yes, the only statistically significant one.
And then also thinking about the superposition, I was wondering, have you done any to look at the height of the jet cores? Because are you doing it all as a regular average, or are you doing anything to look at is the wind speed above your threshold between 300 and 100, or 400 and 100? Because that could kind of show whether you're getting a superposition or if it's just one jet.
Right. I haven't dove into the specifics that much yet. This superposition idea is just kind of first guesses, really. But it would be definitely something to look into specifically.
But your giant ASCII files have that in it already, because one of the
yeah.
other variables is the pressure value.
Yeah,
Where is
so I
the
could-
maximum speed found? So
so I
that's
could go
one
dig it out.
way we could attack that
I
right
just
away.
haven't done it yet.
Yeah.
Hamish.
I think this follows on from Grant's question, but in your histograms, you showed us the bimodal and you called it the subtropical and called it jets and how you could identify both of those. And then sometimes they merge together, but you never named it as a single subtropical or polar jet. I was wondering if that was for a purpose and if you have any inclination of does it become solely subtropical when you lose the polar jet, or is that a wrong way to think about this?
Yeah, no, that's kind of a big question, right? I'm trying to get back to, there it is. So while it does overlap with the subtropical jet in the winter season, I really haven't been able to dive into it enough yet to solidly say whether this is, a merger of both the polar and subtropical jets, or if this is just the subtropical jet taking over. We're not sure yet. That's kind of one of our big question at the moment, is where is this kind of coming from?
Yeah, and that's a really good question, and as you point out, Libby, it's a really great future work question. One thing that occurs to me, though, is that there's not a complete cessation of eddy activity at high latitude in the summertime. So if there really is an eddy-driven jet, as there seems to be in the wintertime, why would it completely disappear in the summertime? But if it doesn't completely disappear, that adds to the idea that this might be a superposition you're looking at, that's consistently happening at like 50 degrees north latitude or something in the heart of the summer. The other thing to keep in mind is that these are results from May through October. If we did the heart of the summer, I wonder if there'd be slight differences on the edges that might make the answer to that question a little clearer. So anyway, that's some of the things we might try.
I'm going to go to Rudra first.
Building on the question, first of all, great talk. Building on the question about eddies and stuff, how important do you think would be the resolution of the emergency dataset that you're using, given that some of the versions you're using has a 1 degree resolution? Do you think a high risk might have subjective results or not?
It could. I know when I ran this stuff I ran this originally on all the data sets without regridding, and it just kind of made everything look like a big mess, especially with ERA, just because the resolution is so fine that you couldn't really tell anything from it. It was a bit messy. So yeah, maybe.
Can I just add a comment?
Yes.
The native resolution of the models that are regridded into their reanalyses may have an impact on mixing in the vertical and other things, momentum fluxes and stuff that can change some of the variables. The reason we had to go to 2.5, adopt the lowest common denominator, is that otherwise you've got Richardson's coastline problem. The coastline of Britain is infinite at small resolution, and it's got a finite value at bigger one. You've got to use the same resolution to calculate contour lengths. So.
Yeah, I was just thinking, so the winter Hadley cell is a lot stronger than the summer Hadley cell, so maybe it's the subtropical jet that actually goes away, and this is just an eddy-driven jet, just kind of,
Maybe.
right?
Because
Yeah.
it didn't.
Possible.
I didn't know
Never
about
thought
that.
of
Yeah.
Yeah, that's
Take that
quite
into
possible.
consideration.
We got to think about that. That's a really
Yeah.
good question, really good point. Tripoli's view was that the polar jet disappears, but he thinks the polar jet is so strongly tied to the polar night jet that, of course, if there's no polar night jet, there's no polar jet. And I've been biased towards that view because I've been trying to get it out of my head. I never thought of that. That's a really interesting idea. So, something we have to think about.
Sarah.
I just wanted to comment again on like the resolution topic of the different data sets, because I think it would be really interesting to see which role it plays, like how the results change depending on the resolution. Also thinking about flammable output and thinking about statements like the jet gets wavier and stuff. So what role does resolution play? Because if we're looking at Horace flammable output and we make like a statement, but then see based on reanalysis data that is really plays like a huge role. So maybe play.
Something worth looking at. Yeah. Thank you. Grant. again.
When you did the analysis originally, before regrading, were JRA and ERA still really similar to each other?
For the most part,
Okay.
sometimes they would throw out totally different values respectively, but for the most part, they were pretty
So
similar
that's
still.
not just a function of the
Yeah,
interpretation?
no, it's overall. And JRA and ERA kind of hung out together, and NCEP was always the outlier.
Were there any trends at that point?
No.
Okay.
Overall, pretty much the same results. Becca.
How sensitive are these jet changes? Like, I don't know, like with sea ice melting, like are we expecting to see these changes in winter too eventually?
Yeah,
Or
that's
is this just like a seasonal based thing?
a good point. I I would have to look into that. I'm not really sure. But that kind of comes back to my question of like, the monthly transitions. Were they always in April? Because, if we're going to enter a much warmer climate, like, could we see the transition happen in March instead of April if we see a longer summertime? Right, so at least in that aspect, maybe.
I think on a related note to that, it would be really interesting to look at the interannual variability to see how much difference there is on the time in year to year, because that might give you an idea of how much internal change there are versus if there might be.
That's a good idea. Joe?
Is there, so you said that little bump at the end of this plot is the polar night jet. Are there other gray bars in there, other different kinds of jets? I'm just wondering like what the minimum 15 or 2 maximum are.
Not really. Those are just, in these columns, there were grid columns that qualified as, jet level winds. However, they're more spread out. They're not like, confined to a structure, right? Like these peak because there are so many columns in this region that it indicates there being a jet stream. Right? So those are just the residual columns that are still dispersed throughout the atmosphere, but didn't really correspond to a jet layer or anything like that.
Any other questions for Libby?
I have a question about the methods, because you introduced several different types of methods from a cultism perspective on how to identify jets, and you gave a good reason of why you used the one that you did for the warm season. But I was curious if, in just the general cultism research, are results dependent on the method that's used, and do you feel like anything that you're saying here would be dependent on how you identify jets?
Depending on the paper, the results do vary. Like, not only with the Manny paper, but there are a bunch of different methods that I didn't get a chance to elaborate on or talk about. But some of them do produce different jet results, some contradictory in some cases. As for mine, I think this is a fairly robust method. It objectively identifies the jet and the isotope, which some of these other methods don't do. So I think this is fairly decent, but I also might be biased.
It's a really good question, because there's a collection of results of characteristics of the jet that you can get from using this method. It makes it attractive. The main impetus was to try and have a robust way of measuring how wavy the flow is. But then other things fall out of it. The average wind speed, the latitude, and the equivalent latitude is not quite the average latitude, but it's close. So it's really hard to say, if the Manny et al. Work would show similar things if you took the results and said, let's see if we can figure out how wavy the flow is. I don't know what the answer to that question is yet.
Okay.
And the same with Archer and Caldera, and then also,
The monitor.
there's a guy from Stanford who did some work with this, the level of maximum wind speed.
Yeah.
There's another method. And so all of those things have not really been looking at waviness, and as a consequence, it's hard for my limited perspective to understand what they might mean. But it's a really good question, and I suspect underlying methodology choice, there's going to be some differences in results. But hopefully hopefully the main points are robust enough to survive that, but I don't know that that's the case.
Great. Again.
I think if you're already separating it into basins, looking at waviness, it makes a lot of sense to also look at over land, because there's a Hoskins paper where he showed that summer versus winter, there's a really big difference between orographic and thermal forcing of eddies and which one is most important. So I think if you can show that, there's no trend over land, but there is a trend over winter, that can say something about that.
That's a good idea too. I'll remember that. And
I was wondering if you have any further thoughts on why the NCEP reanalysis is so different
that's something that I've kind of thought about a lot. It doesn't really take into account the satellite data, I believe, so that might be what's helping improve the other two data sets. But overall, I've learned that it's kind of regarded as maybe not the best data set, so that might be why there's so many of these differences. So while it did, catch similar interannual variability patterns, it just had the, base values worse overall. Ruja.
sorry, I have a very one last random question about nuclear figures.
You're good.
It seemed that during the last 20 years, 2020s, there was an increasing trend in the waviness.
Yeah.
However, you also mentioned that the jet core is also increasing, like the wind speeds are increasing. Does that mean that the jets are getting faster and they might not be getting wavier? Like, could you piece that together? Because if it's getting wavier, then it should be getting slower, or that's not the case.
I don't know what to expect there. I respect
I don't know.
I respect the question a lot, because I had in my notes, the ERA 5 speed trend is significant, the ERA waviness trend is significant. That means the circulation, as featured in the ERA 5 of reanalysis, is intensifying in the summertime
Right.
at the jet core. How does one explain that? I don't know nothing comes to mind right away. Why should the summertime jet circulation intensify around the hemisphere? I don't get it. So it's a question that's out there, and I think the same thing could be said about the wintertime, where the speed of the polar jet and the waviness are increasing. How do you rectify that? How do you say in a warming climate the circulation is getting more intense? It's a conundrum. So I don't know the answer.
True.
I have another question about these kind of distributions. Do you see over time if when they merge and they separate is changing? Like, is there a climate change signal in when the jet?
Not in the time frame that I looked at specifically, but that's, kind of also the problem that I left for future work, right? I want to see if it's, evolved over time, always been at that one specific mid-April spot or not. But from what I have looked at so far, and I have looked into that question just a little bit, kind of ran out of time, but they seem to kind of be. I'll have a more solid answer for you on that further down the road.
Okay, if there's no other questions, let's thank Libby again for stimulating the conversation.